Thank you.
Sure. Okay, so we talked about Lewis dot structures. Now we're going to talk, and the problem with Lewis dot structures, they're two-dimensional. And the world is not two-dimensional, the world is three-dimensional. So we're going to talk about the next level of theory to predict the actual three-dimensional shape. That's called valence shell electron pair repulsion, or VSEPR. Okay, so basically, we've got to look at a couple things here. The one thing you need to get down to start with is going to be something called a central atom. In fact, let me erase all this stuff here. And that is something called a central atom. Now, all this analysis is done around the central atom. If you have 3 central atoms in your molecule, you have to do 3 analyses. Okay, so central atom. We're not doing analyses on anything but central atom. So what is a central atom? Central atom is an atom that's bound to 2 or more other atoms. So let's look at, for example, which is the central atom there? Hydrogen or oxygen? Oxygen. Okay, the hydrogens are not central atoms because they're only bound to 1 other atom, okay? So how many analyses will we do with water? 1. Okay, that's acetic acid. How many central atoms are in acetic acid? Okay, we've got 1, 2, 3. The 2 carbons and 1 of the oxygens, because the double bonded oxygen is only bound to 1 other atom. So those are the 3 central atoms. Okay, so all the stuff I'm going to talk about now in lab is around central atoms. So if we were to do an analysis of VSEPR analysis of acetic acid, we'd have to do 3 analyses. Now on your test 3, I'm going to give you a simple molecule with 1 analysis and a multiple central atom where you're going to have to do multiple analysis, okay? So focus on looking at the central atom. Now, once you focus on the central atom, you're going to use your fingers to cover up what's not attached. So for example, now I'm going to do my finger in blue. Those are my fingers. So we're just focusing on the oxygen, and oxygen has That's what oxygen looks like. So we're going to focus on the two bonds and the two lone pairs for analysis on water. Okay, so central atom, very, very important in this unit. Okay, the next thing we're going to look at are something called electron groups. Now, depending on what you're looking at, they could be called electron groups or electron domains. Electron domains is the fancier word. So depending on what you're reading or looking at, you'll either say electron domains or electron groups. I think groups are more intuitive. And when I say groups, it's groups of electrons. So if we were to look at carbon dioxide there, first of all, how many central atoms does carbon dioxide have? One. The two oxygens are only bound to one atom, so they don't qualify as a central atom. Okay, so we're going to cover everything except the central atoms associated either electron pairs or bonds. Okay, so let's look at this. Now, how many groups of electrons do you see up there? At first, this is a tricky question. How many groups of electrons? Oh, how many? No, not 6. There's 4. I hear any other number? Going once, going twice. 2. Okay, 2 is correct. One group, one group. So this molecule has 2 electron domains or 2 electron groups. Okay? Triple bond is a group of electrons. So a single bond, a double bond, or a triple bond all count as one group. If you have 2 groups, you're going to have a linear molecule. Linear. Now, I want you to think about this now. The name of this process is called valence shell electron pair repulsion. What do electrons want to do when they get one next to one another? They want to repel. That's why this process is called valence shell electron pair repulsion. They want to repel. Okay, so the most stable place for those 4 electrons on either side is to be exactly opposite. Think about a family, and they have 2 bratty kids that are fighting. And what does the mother want to do? They want to separate them. They want to put them together. They want to put them in opposite rooms as far apart as possible for that mother's sanity. Okay, so they want to get as far apart as possible. And that's with 2 sets, that's in a linear configuration. The angle is 180 degrees. Now you're going to have to know angle, geometry, how many central atoms, how many electron groups. Okay, so for carbon dioxide, we've got 2 electron groups, 1 central atom, geometry is linear, the angle is 180. Okay, now there aren't very many linear molecules out there. Most molecules are more complicated than this. All right. Formaldehyde. How many central atoms does formaldehyde have? 1. The oxygen is bound to 1 atom. The hydrogens are bound to 1 atom. So the carbon is the only one that has more than 1 atom attached to it. So 1 central atom, that means 1 analysis. Okay, so now we're going to cover all the atoms attached to the central atom. How many electron groups do we have there? One, two, three. Three wins. Okay. We've got one group here. Three groups. When we have three groups of electrons, the geometry now goes to, remember, the bratty kids. We have three kids fighting now. We have to separate them again. So we need to spread them out as far as possible. And because the kids are all the same age, they kind of are bratty, the same level. So we're going to separate them in equal chunks. And that angle is 120 degrees. Okay. Say again. Now, you are competing with this blower up here.
Okay. What mole?
Oh, it's formaldehyde. Formula? Chemical for what?
Yeah. That's the way. Like it's like CO2. Periodic.
Oh,
Yeah.
no. Why do you think it's not on the periodic table?
No, no. So like the other one, that was CO2. What is formaldehyde? How is that? How is formaldehyde H2?
You mean the formula for formaldehyde? This is the formula here. Okay. All right. Now, the angle is 120. Now, every time I give you an angle, that is assuming that the attached groups to the central atom are equal. Basically the same atom and the same bond. It'll be 120. Life is not like that. Frequently, it's not the same. They're different. So formaldehyde has got one double bond, two singles. So those bonds are not equal because the double bonds is a little shorter than the singles. So its influence is more than the single ones. Triple bonds are even shorter yet. So the bond angles for formaldehyde aren't 120, 120, 120. They're distorted. It's called bond distortion. Now, I'm not going to ask you what the distortion from 120 is. I might ask you, is it 120? Your answer would be yes or no. Okay, I'm going to go one level more. And that is we have 4 electron groups. An example here is methane, CH4. And methane is a nice example because the atoms attached to the central atom carbon are all the same. They're going to have equal influence. So the bond angle is exactly 109.5. So we've got 3 angles we need to know for this. 180, 120, and 109.5. Now in 1A, we go even 2 steps more. We go to 5 electron groups and 6 electron groups, and things get much more complicated. And that's for you to know that it gets wilder the bigger the number of electron groups go. We're only going to 4 though. And it's important you understand those 4 groups though. Okay, so now linear is 1 dimension. Trigonal planar with 3 groups is 2-dimensional. Tetrahedral is 3 dimensions. So the best way, it's not 90, 90, 90, because there's a more efficient way to spread out that repulsion by going to 109.5 in 3 dimensions. So that looks like a little pyramid. Now in lab, theoretically, we're going to have model kits, and you can actually build one of these and look at it. Okay, so trigonal planar. Now it's important on this trigonal planar because we're also going to have one called trigonal perimeter. There's trigonal planar, trigonal perimeter. Easy for me to say, right? All right, so now what I'm going to focus on now is there are 2 kinds of geometries. One's called electronic geometry, and that is called molecular geometry. And they're related, but not the same. And what I've been describing up to this point has been electronic geometry. That's the geometry of just the electrons, not the atoms at all, just the electrons. How the electrons distributed around the central atom, linear, trigonal planar, or tetrahedral, like 3 variations. Molecular geometry, if we had a super duper microscope, we could home in on that central atom and look at it. We could see the atoms attached then. That shape is going to be the molecular geometry. Bless you. Okay, so this is what we're going to do in lab today. Step 1. You need to draw the Lewis structure. That's why we spend so much time Thursday practicing Lewis dot structures. So step 1 is Lewis dot structure. If you mess up the Lewis dot structure, guess what? The rest of the problem is going to be wrong. So it's crucial you understand how to draw Lewis dot structure. And remember, there's alternate shapes also. If the alternate shapes are legal, the VSEPR analysis may be different. As long as it's a legal structure, you can do legal analyses, some cases. Okay, so step number 1, draw the Lewis dot structure. Number 2, per central atom, count the electron groups. For the electron domains, 2, 3, or 4. Okay, that determines the electronic geometry, either linear, trigonal planar, or tetrahedral. So once we know the electronic structure, that will lead to the molecular structure. I heard nothing of what you. Okay, she answered your question. Okay, thank you. Okay. So that's the first step, is to determine the electronic geometry. So we find the central atoms. We look at the number of electron groups around the central atom. It's either going to be 2, 3, or 4. Unless you're in Chem 1A, then it'll be 2, 3, 4, 5, or 6. Okay. And then that leads to an electronic geometry. If it's 2, linear, 3, trigonal, planar. Planar means flat. Trigonal means 3. Tetrahedral, tetra is 4. Hedral means pyramid-like. Okay. Now, let's look at something that's a little different. Let's look at water. Okay. How many central atoms does water have again? 1. Step 2 is draw the Lewis structure. Now, your Lewis structure could look like this. It could look like those are all valid Lewis structures for water. One of them is correct, though, based on the valence shell electron pair repulsion, or VSEPR. Okay, so number 1, we have the central atom oxygen. How many electron pairs are around that oxygen? Electron groups, yes. How many? Doesn't have to be bound to be an electron group. 4. 4 electron groups. We have remember now, we're ignoring the atoms attached. So we've got 4. So based on what we've already discussed, what is the electronic geometry of water? Is it linear, trigonal planar, or tetrahedral? Tetrahedral, because it's 4. Four electron groups. Now, in this case, so H2O got 2 bonds, single bonds, and it's got 2 unpaired electron groups there. That's where we get the 4 groups. Now, notice that there's no way the hydrogens can be linear because they're on a lobe of that tetrahedron. Okay. So step 4 going to be determine the number of bonding and non-bonding groups. Bonding groups mean there's an atom attached. In the case of water, that's those hydrogens. Non-bonding means that's a lone electron pair that's not attached to anything. And that determines the molecular geometry. Now, sometimes the molecular geometry and the electronic geometry are the same. Whenever we have 0 non-bonding pairs, they're the same. If those are different, then the molecular geometry is different than the electronic geometry. So the electronic geometry of water is tetrahedral. But in the case of water, we've got 2 and 2. Whenever we have 2 and 2, that's bent. Let's look at ammonia. Ammonia is NH3. It's a gas. When you dissolve it in water, it becomes ammonium hydroxide or ammonia water, which is you buy at the store for cleaning grease. It's a mild alkaline or basic solution when you dissolve it in water. All right, so first step is Lewis dot structure. How many central atoms do we have here? 1, correct. Okay. Okay, so how many electron groups do we have? 4. So what's the structure? Electronic geometry. Tetrahedral. Electronic geometry is tetrahedral. Now, to determine molecular geometry, we need to find out how many bonding and non-bonding electrons we have. Okay, so how many bonding electrons do we have? 3. That's the NH, NH, and NH. And how many non-bonding? 1. When we have 3 bonding and 1 non-bonding, that's called trigonal pyramidal. So it's a pyramid, but it has 3 sides rather than 4 sides. So it's trigonal pyramidal. And that's what we're going to do in the lab today. We're going to practice the daylights out of this. This is not hard. It just takes, there's a lot of little details you have to pay attention to. Now, another question they always ask, is this a polar or non-polar molecule? And there's all this long verbiage on how to determine that. Ferguson's verbiage is very short. Is it balanced? Yes or no? If it's balanced, it's non-polar. If it's unbalanced, it's polar. If it's skewed to one way, it's going to be polar. If it's perfectly balanced, with atoms all being the same, it's non-polar. Okay? So let's look at our examples again here. So what do you think about ammonia? Is it balanced, symmetrical, or is it skewed? Not balanced. We've got an unpair of electrons and then 3 bound electrons. So it's not balanced. It's lopsided. So it's not symmetrical. So what is it? Polar, nonpolar? Polar. What about water? Polar or nonpolar? Is it skewed to one way? Yes, it is. So it's polar then. In fact, water, because it's so skewed, is particularly polar, more so than ammonia. Now, let me give you a little hint on this. Yeah. Or water, what? Molecular geometry is going to be bent. Now, in your lab tonight, you'll have a chart, and I'll show you all these combinations. So water is bent. Whenever you have oxygen single bonded, write this down, it's always polar. There are a few exceptions, but 99% of the time, polar. Now, I didn't say double, I said 2 single bonds, like water, like alcohol, like sugar, like cholesterol. A whole bunch of oxygens around that are single bonded, and those are all polar. Acetic acid. Okay. Okay, now we're going to get used to drawing 3-dimensional objects on 2-dimensional paper. Okay, you've got single lines there. That means those H's are in the plane of the paper. The little triangles means that H is out of the paper towards you. The dotted means it's on the other side of the paper. Okay, so dotted is in the back, triangles are in the front, single lines are in the same plane as the paper. Okay, so polar, nonpolar. Nonpolar, why? Yeah, the same atom is nice and symmetrical. No, not skewed one way or the other, no oxygen there. So it's non-polar. Now, this really comes in handy in biological systems. Our body is a big sack of water with a bunch of stuff going on. And our body tries to separate those water-based reactions with something called who's had biology? Okay, how does our body separate those water regions in a biological system? What surrounds the nucleus? Membranes. Exactly. See, you can do that. That's what our body does. Okay, so water reactions are very polar because of water. Membranes separate the water reactions from one another by having a non-polar barrier called a membrane. Fancy word for that is a phospholipid bilayer. That membrane is very, very nonpolar. So the water stuff stays on one side of the membrane or the other side, not in the middle. So our body has tens of thousands of membranes set up around the cell, around endoplasmic reticulum, around the nucleus, all these areas of the cell that require separation from other parts is surrounded by a membrane. And then our body cleverly has holes in the membrane that our body can turn off or turn on. It's called active transport or active transport or inactive transport. And basically they're holes in the wall. We can turn those, we can open those up, and turn them off. Our bodies are very clever that way. But bottom line is the separation is because of polarity. Polarity. A nursing student of mine about 5 years ago sent me an email. She was in the middle of this heavy duty A&P class, anatomy physiology class. And they were talking about active transport on membranes. And they had a calcium molecule there. And she goes, oh, calcium is polar. So she's telling the instructor, well, this can't go through because it's polar, all that stuff. And it all came from our chemistry class, talking about polarity of molecules. It was nice to hear from some of my past students. All right, so that's what I want to cover as a front end to our lab today. Okay, so you're going to be going through and figuring out polarity, electron, geometry, molecular geometry, central atoms. You're going to practice that at the yin yang. Also, you'll be practicing your Lewis dot structures as well, since that's step 1. Okay. Now, has anyone not claimed their tests? If you haven't claimed your, is Juana here? Okay. Yeah. With your initials on the back. All right, so that's what I have for today. I'll meet you all in lab. You may go to Thursday's lab or tonight's lab. I don't care. Mix it up. You can work in the hallway. You can work in the lab. Actually, you can work in here too. Oh. No, we're going to start right now.
Okay.
Well, as soon as I get over there.
Then I'll come for a little today, and then I'll be there all day. I still have my lab packet, so I'll pull it up on my phone.
Yeah, that's fine. Yeah.